So my name is Mohammed Nasser Azadani, and I got my PhD from UC Santa Barbara. And I've been with Accenture for almost 4 years now. I've been with Accenture Labs for 2 years, and I've been leading the enterprise AI effort. Today you're gonna hear also, we're gonna co-present with Yao Yang and Andrew Nam, my other team members at Accenture Labs, who contributed to this work for the last year, and almost a year and a half, this work to this point that we were able to publish our algorithm and file a patent. So very excited to show it to you and get some feedback. I just for the logistics want to say that this is going to be a presentation covering a little bit of a high level what the real need and kind of the business driver behind this work. And then afterwards, we're going to get into the algorithm and our solution, and then some validation and results at the end. So feel free to ask questions or type. We are going to be really flexible. So if you, I leave it up to you how you want to moderate it, but ask questions. There is no bad questions. So can you go to next slide, please? Just before diving into talk, so Accenture, if you know the company, it's a consulting company, and we are pretty much a ginormous company offering services worldwide. I think close to 500,000 people. Surprisingly, our R&D piece, which is Accenture Labs, is very small. It's roughly 200, 250 people worldwide. And these are the cities across different countries that Accenture Labs has presence. Essentially, our mission is to do applied research aligned with market and the needs of the client. So something between more or less academic research and really kind of a market value. So we don't always work with clients. We sometimes do, but we are more focused in terms of shaping the next 2 to 5 years of what technology has to offer and help our company and also the clients. Next slide, please. So the overview of this talk is we're just gonna talk about the open problem, about the automatic machine learning and the 2.0 version of it because of the new needs in the market and some of the current solutions. And we're gonna get into our algorithm, the Resource-Aware platform, and then essentially talking about some validation and some experimental results and with some summary of the future work. Next slide, please. All right, well, the audience here, I'm assuming you have either some background in AI machine learning or you are an enthusiast. So we're gonna, I think some parts of this will get more technical, but some part of it is for more audience. So don't get disheartened if some part of it get details. But the first, just going into the machine learning and automatic machine learning, I think machine learning, as we all know, it's really driven by performance, and the performance has all these different meanings in terms of accuracy, and accuracy has all these different ways: precision, recall, F1 score, you name it. There's hundreds of ways of measuring how good a model is performing. But over the years, it seems like accuracy is not enough in terms of the actual need for production settings and a wide variety of clients or type of people who actually use it. But the focus and the research of the academia, look at this plot, like how much this is essentially showing, you know, that to get the more the better loss, how many layers, or like how the size of the network is becoming more and more ginormous. It's just because the focus is only on accuracy, and the other things are it hasn't been problematic, but now with the size and the resources it needs to be trained, it is actually becoming problematic. You might have heard right now there are some neural networks like this one, the NLP, the transformer one that I believe Google had introduced a while ago. Just to train it, it actually did an estimate of it needs 5 times of the lifetime of a car. and the energy and the carbon, the carbon CO2 carbon that it produces. So you can approach that from different views, right? One, you could say, well, it is maybe it's expensive, even if you don't want to think about the environment impact. But you could also think about the implication for the businesses. Essentially, not many businesses have that many resources or the budget to do that, right? It may cost millions of dollars just to run it once. And it is not necessarily good news for the deep learning businesses, because then essentially only 4 or 5 companies on the entire planet can afford training that, if the trend continues to go that way. Can you go to the next slide, please? So I guess naturally some questions are arising lately, which is, you know, how do we build machine learning model, and more precisely automatic machine learning, that also start honoring resource constraints? And for that, there has been a lot of interesting work and research doing that. But I think you're going to see that this has a lot of interesting implication, and will provide some flexibility on how to do that. So in the context of a case study, let's think about it. Like, if you want to deploy an image detection or object detection model on, let's say, a drone, accuracy for the model is not only going to be enough, right? There are new aspects of this model that are going to start becoming important. One is the inference time. Like, let's say this drone is a security drone that's surveilling the area. So you cannot wait forever for one object detection query to say this was an intruder or this was a truck versus not. The other aspect is like maybe memory consumption, because the hardware that are installed on this type of drones, they're limited. Maybe there are special types of FPGAs, or even the battery could be another issue. Like maybe if the model is too big and it uses too many neurons, the power consumption is going to be big, and that way essentially you're draining the battery life. So these are some interesting questions if you think about it, that maybe they were not that important for the machine learning folks or the data scientists when they were building the model back then, but now they have to begin think about it, because the process is not also linear. Because oftentimes it used to be like that people would first train a good model, then hand it off to like a platform engineer for deployment. But now things are becoming more and more interesting in terms of trade-off between different objectives. And sometimes these goals are competing, that you actually have sometimes to think about everything from the get-go and when you start training the model. Can you go to the slide, please? So just to recap, I'm sure you all know AutoML, or automatic machine learning. It used to be agnostic to any resource or hardware requirements, right? The primary goal was, we have this complicated, let's say, search space or hyperparameter search space for, like, let's say, a deep neural network. And essentially, all we care about is having the best model, and best meaning like most accurate model. And like, if back then you had some resource issues or hardware constraints like that, usually these questions would come after the fact that you already trained the model. Like, as a simple example, like oftentimes, and it is an interesting active area, that people train a good model, a ginormous model, but then depending on the size of the hardware they're using, they will actually prune it down such that it can still fit on the reduced hardware. But as you see, as we mentioned, these things are getting a bit more and more complicated, and pruning is not going to be enough. Can you go to the next slide, please? So for the folks, experts in the deep learning community, or have some exposure, essentially just think about the purpose of the slide is to kind of remind you of like the complexity of the AutoML itself, even without consideration of resource-aware. You know, the hyperparameter search space, meaning all the choices that an engineer can have before even start training the model. Like the simple example of object detection, the human versus minion, you have to make decisions about the type of convolutional layers, the pooling layer, fully connected layer, the activation function type. And these are not even the regular parameters, right? These are hyperparameters that usually engineers with their own experience, they actually have to make the call, and they're not 100% sure that it's the best call, but they usually do, and then they apply AutoML. So that for itself is already complicated. But then, can you go to the next slide, please? But then, like, subjecting it to other constraints would be even make it more complicated. But you could ask us like, hey, why don't you, if you can do this automatically and do this search, but via AutoML, like you define a complicated search space and then just let the algorithm find the best model. To that, yeah, you're right. That's an easy way to do. I guess we wish we could have done that, but you already know some of the challenges there. Like if you have too many hyperparameters, essentially your search space becomes very high dimensional. And searching any high dimensional space, I'm not a mathematician. It usually has its own challenges. It comes with convergence issues. It may take even years to find that, even with good plus it's always expensive. Is there a way we can do this faster? You can go next slide. So like think about how you can construct that search space, right? Like during different parts of the building the model, you have to define some hyperparameters, like maybe some of them are architectural, the number of layers, the layer type, kernel size, even during training or even during the evaluation. These are all the decisions or hyperparameters that could potentially go into constructing your search space. But usually good and well-experienced deep learning engineers are the ones that actually just make the call to pick the ones and simplify the search space. But this was already complex, as you already saw, right? And now the added complexity is, okay, what would you do in this whole process of using the data pre-processing, feature engineering, making decisions about model architecture or training the model? Like these are the high general tasks. Like if you want to automate it such that it can also consider other things, it seems it's going to be an interesting, complicated things, and a lot of human decisions has to go into it. And those human decisions, as enterprise has been starting experiencing it, it's not limited to the data scientist or machine learning engineer anymore. The platform engineer folks are going to be pulled in and all that. Can you go to the next slide, please? Yeah, so this is a little bit of the state of the art right now, and I'm sure it's not going to remain that way. It's going to change sooner or later. That to have a full-fledged product, meaning the machine learning model, that we obviously want to use AutoML to find the best one. These are the decisions that have to go into the entire pipeline. And essentially to still, again, as I mentioned earlier, right now we still are doing this more or less in a linear fashion, meaning that we isolate data scientists from maybe the firmware engineer limitations and vice versa. Because it makes sense, linear is easier to do and it's repeatable, but ideally, some of these folks have to be talking to each other. And maybe if data scientists already knew the maximum amount of memory that the model needs to run on, maybe she could have actually limited the search space in a different way. Can you go to the next slide, please? So I guess any resources and we're using this in a very abstract and general way. It could be a manifestation of hardware consideration. So like, the memory or the CPU, GPU, it could be truly like the budget. Maybe you only have 10 grand to run and train a new model on the cloud infrastructure you have. And it can manifest itself everywhere. Interestingly enough, it has made the process flat, as we showed in the previous slide. And more of the engineers and data scientists has to be involved to meet these resource constraints, as opposed to before that they could have been isolated from the other section. Can you go to the next slide, please? So in order to start building a pipeline for automating machine learning with resource constraints and multiple goals, we need to start thinking about, okay, so some of the typical resources, how do we do that? How do we measure them? How do we assess them? And a lot of them are related to the model performance. So the number one approach is actually a model-based approach, meaning that it is agnostic to the hardware that the model is run on. And it is essentially because we know all the linear algebra, we know all the weights and the layers and whatnot. They're essentially gonna go through the model and do the multiplication, matrix multiplication. So you can have proxies for that. You could say, well, every summation costs a flop or whatnot. And then there are a lot of papers that actually go to the details of that. But the nice thing about the neural network architecture is like essentially you can feed in this entire configuration that let's say you hypothesize, and you can get a good estimate, a pretty good accurate of the number of operations in the forward inference or backward that went to get an estimate or the forward inference or classification. And with that, you can start adding more and more layers of proxies. So with maybe the flops, now you can multiply it by the type of infrastructure you're working on, maybe an AWS instance, and you can translate it to the cost or the latency and whatnot. So I like this approach because I think it's strongly mathematical, it's repeatable, but it also has its own limitations, as I'm sure. The nuances of different hardware architecture is not going to manifest themselves here. So that's why a lot of other people also prefer the approach number 2, which is essentially measuring using accurate profiling unit to measure the same things, but in actual runtime and benchmark. And you could be an advocate of either of those, or maybe a hybrid one. And we're not saying any of them are better. Just have to know what you're using these for. So with that, I think I'm just going to set the stage for Yao to say, okay, well, now we were able to measure these things that are usually now typically of interest of machine learning 2.0, if we will, accuracy plus a lot of other interesting constraints or hardware limitations. How can we actually refactor AutoML in a traditional way, in a new way to honor that? So with that, I hand it off to Yao.
Hi, thank you, everyone. I'm Yao, research scientist of Accenture Labs. So thank you, Mohammed, for giving us this introduction. And we know that there's this space that has a lot of technical and business importance that we haven't tackled yet. And as a lab, we are looking ahead, and this is something that we have observed in our client practice. And we were trying to figure out and propose our own method to solve this problem. So I will show you guys how we frame this problem into a solvable mathematical engineering problem and how we build our tool. So to break the problem down, there are 2 layers, right? So essentially, this is a multi-objective optimization problem. We are trying to find the best model. And how do we define the model? There are competing objectives, right? So that's the first one. There are a lot of like optimization methods. In our case, because the models, they have mixed parameter types. Let's say they have like continuous variables, categorical. The cost function is not necessarily like in the convex format. So the traditional gradient-based optimization techniques can fail, provide a non-optimal solution. So we are motivated to look beyond kind of more gradient-based optimization method. So the second layer of the problem is to incorporate the constraints into the live AutoML process, right? As we have mentioned, as Mohammed has mentioned earlier, the existing solution trains the model, and when thinking about kind of need to deploy it on edge devices, we will prune it down. So how can we incorporate the constraints from the beginning in the live process? There are a few methods that we've seen in papers and practice. The first one impose constraints on hyperparameter search space and keep the optimization cost function not changed. The second method applies the kernel function to constraints and the original cost function and derive a unifying cost function which maximizes the model accuracy while honoring the other constraints. But but these methods, they don't take into consideration of the multiple objectives. So in our method, we kind of redefines the problem such that the constraints and the objectives are now represented by new objective function. And these new objectives, along with the original primary cost function, which is focused on the accuracy, all these cost function will be optimized simultaneously. And have that being optimized, we will have a Pareto front of the best model candidates, and the user can pick the best model from the Pareto front when there are multiple possible models available. Yeah, so our approach is a 3-stage process. We first translate the business objectives like accuracy, latency, inference time, memory consumption, etc., and the constraints. For instance, on the edge device, the memory consumption cannot be exceeding a certain amount, or the inference time has to be smaller than, let's say, 30 seconds, right? So we translate these objectives and these constraints into mathematical optimization problem. And for the second stage, we this is our proposal here, and we use a modified Bayesian optimization together with a genetic algorithm, which solves the multi-objective optimization problem. So we combine those to search for the Pareto optimal solution. Having the Pareto optimal solutions, we will then suggest the best solution to the user. And a component here, we use the distance-based algorithm, TOPSIS, to help us choose the best solution. But the user can also decide the best option by themselves. Think about like a slide, they can put more emphasis on accuracy versus memory use, right? So they can choose which objective they want to put more emphasis on and choose the best option by themselves. Yeah, so Andrew, I'll leave the floor to Andrew now. He will go into details of the architecture of our solution here. So Andrew.
Thanks, yeah. In order to understand our design of our solution, first we need to understand the tooling we use. So the first method that we use is Bayesian optimization, or in our case, a modified Bayesian optimization. But I want to begin with a recap of what standard Bayesian optimization looks like. So Bayesian optimization uses a Gaussian process to approximate a function. You have a certain number of observations, and it uses those observations to estimate the function. So in the figure here, for example, we have the true function, which is the green dotted line, and then the x, or the solid black line, is the approximated function based on the observations that it has. In Bayesian optimization, the Gaussian process also gives us a measure of uncertainty in different areas, and we use that to measure an acquisition function, which is typically a function that gives us indicates where we get the maximum information gain. So that's the red line that you see down here. So in Bayesian optimization, you would maximize your acquisition function at the end of each step, and then you would select that next point to observe. You collect that observation and repeat this process. Now, in our modified Bayesian optimization, what we've done is discourage exploration in a certain area if it is violating a constraint. So this does require us to have a way to know if we are violating a constraint. So we have built in a constraint predictor, and then we mask this acquisition function simply by setting things values to 0. Since it's a maximization, setting them to 0 helps discourage it as much as possible. So here's sort of, I guess, a more mathematic representation of our process, and also sort of really demonstrating the impact of our modified acquisition function. So on the far right-hand side, you can see in the middle, we have a hard constraint. So in that area, we completely discourage exploring that area because we are violating the constraint. You could also use this approach to enforce a soft constraint. which would be a constraint that penalizes generally with increasing penalty the more you're violating the constraint. In most of our experiments, we used the hard constraint, but we did demonstrate that soft constraints also worked. And this is also just to demonstrate, oh, we can move on. Yeah. So to look at a more systematic view of our modified Bayesian optimization. So our inputs is our data. So that's our observations, our constraints, and then our objective. And objective is what are we trying, is the function that we're really trying to understand. This Bayesian optimizer has these three components: the actual Bayesian optimization component, the constraint predictor model, and the model simulator. We call these plug and play units because they should be swappable. We provide an interface in order to standardize the interactions with our modified Bayesian optimizer. But it makes sense that these are respective to the experiment that you're conducting, because you're parameterizing in a certain way. So there's certain hyperparameters that you are optimizing in each experiment. So those are the parameters that you would want to be reflected in your simulator as well as in your predictor. And it'll maybe make a little more sense on the next slide as well. So this is our overall system architecture. So these are the different objectives, or the model objectives that we talk about, are the different things that Yao and Mohammed alluded to, such as accuracy, but now also considering things such as how much memory are you using, what is your inference time, etc. You have the actual data that's being used for the experiment, the constraints. So these are things that we don't want to violate. Like Yao mentioned before, we don't want to have a memory over 100 megabytes and an inference time greater than 2 seconds. And the search space is the representation of the experiment. And what that means is how have we parameterized the model, like I talked about previously. So what hyperparameters are we optimizing, and what is the area that we're optimizing them over? For example, for dropout rate, we would put a range from 0 to 0.5. For number of layers, we would maybe use a discrete set, so 1, 2, 3, 4. And maybe if we have something like activation function, we can use categorical variables for the different activation functions we're using. You also provide a stopping criteria. And generally the stopping criteria, can you go back to the previous slide, yeah? The stopping criteria is a number of iterations, but you can use more advanced values like a distance. And now stepping through our process. So we have our simulator here. So again, the simulator is respective to the search space. So we want to be able to construct an actual model and then measure the values that are of interest to us from that model. What we've done is built sort of a set of generic simulators that capture everything that we need, one for TensorFlow and one for PyTorch. But that you could use this approach and have custom simulators for each experiment if needed. For our modified Bayesian optimization, so how are we doing this over multiple objectives? So we have a Bayesian optimizer for each objective that we're trying to optimize on. So for accuracy, memory, and latency, in that case, we would then have 3 Bayesian optimizers. And now we run into issue of, in Bayesian optimization, we maximize the acquisition function, but now we have 3 of them. And that's why we use our multi-objective optimizer, NSGA2, in order to build, in order to do multi-objective optimization, build a Pareto front, and then TOPSIS helps us select that, the best solution. NSGA2 is a genetic algorithm, and TOPSIS is a distance-based algorithm for best fit. We repeat this process over and over again. So the best configuration essentially selected by this multi-objective optimization of these acquisition functions will now be simulated in our simulator. And we will take these observations and continue to process. For our simulators, we've actually done a variety of experiments, both on CPUs and GPUs. And we've also actually built sort of a cloud based simulator on AWS that looks at, again, different AWS instances and allows us to experiment on those as proxies as well. Once you reach your stopping criteria, you reach your exploitation stage, this right-hand side. And what you do is now we have all our observations. And in Bayesian optimization, it's not necessarily like gradient descent where you're consistently getting better, hopefully, or generally. It's more explorative. Sometimes, even if it's found what's near the best solution, it might look for other solutions after that. So that's why we build another Pareto front with the objective, with the values that we've collected. And now we can use Topsys again to select the best one, but we can also just provide that information to the user. So the way that that reflects back to a user is you have this set of model configurations that have these trade-offs between the objectives that you chose. So maybe one is strongest in accuracy, but like we showed before, maybe it uses way too much memory and therefore also has a very high latency. But there's maybe another model that sacrifices on accuracy a bit, but performs better in the other areas. And we were able to validate our multi-objective process using just generic functions. And it was comparable to, or was able to find the front for these complex functions. And I'll throw it back to you, Yao, now to talk about some of the real experiments that we've done.
Thank you, Andrew. So in order to test that this whole workflow, this proposal works, we've tested this on real data. We run the real experiments. So kind of a concept here is AutoML. Like, how do we? What exactly is automating, right? So a lot of kind of the low-hanging fruit, the easiest approach is to do hyperparameter search in transfer learning. So identify some of the base models like VGG16, VGG19, ResNet. So all these models have already been trained. So we identify the hyperparameters that we want to fine-tune. So we redefine a search space for that. So that is the experiment one, which is based on transfer learning, and we run hyperparameter search on a bunch of on a few candidate models. Experiment two, which we started to explore, how do we build model from scratch? It's a rather complicated field. There are various ways to solve it. We have decided to kind of follow the same workflow that we have. And decided to use basic building blocks, right? So think about basic building blocks as, let's say I identify 5 basic building blocks, and essentially what we have, the search space is different configurations for the building blocks. Okay, so we have the experiment 1 and experiment 2, they would have the same workflow, which is to first identify search space, and we do the modified Bayesian optimization, getting Pareto from select the best. So these are our 2 experiments, just to clarify. So we have run our algorithm on CFAR10 data. They have 10 objects to detect. And the objectives here, we have accuracy, which we use top 5 validation error as a way to for accuracy. We want this error to be as small as possible. We also want to minimize the model memory consumption and also the forward inference time. And here we use the flops as a proxy. And the 2 experiments, we have different constraints for them. And this page shows the result of the 2 experiments. As you can see from the graphs that we have the 3 objectives, and we can see the different trade-offs among different objectives. So in experiment 1, the search space we have identified is, we have base model being VGG16 and 19. We have a few hyperparameters like dropout rate, layer, number of layers, batch size, what kind of activation function to use. and we give a range for all these hyperparameters. And for experiment 2, we use 2 kind of basic building blocks. They're modified from ResNet. And we also have the other hyperparameters like block depth and learning rate activation function. So both of the experiments, we have seen that they got comparable results from the known deep learning models. As you can see, the top 5 error rate is equal to or even smaller than ResNet 18 and 34. And at the same time, we can account for memory and flops, and they are within the constraints that we have set. So some of the future work here, we have built a prototype for a solution that we propose to solve this problem. And for the next step, we wanted to improve on the building blocks of the neural architecture search algorithm. We have used very simple ones, ResNet block, and we have modified a block from that. So we wanted to put more thoughts on the building blocks as to improve an NAS algorithm. And we also wanted to figure out whether we can use similar workflow in other NAS methods, not just in this building block method. And the third field, which is something that we have already started doing, is a resource prediction twin. It helps us to profile hardware and expand the workflow to the actual model deployment, giving users a suggestion on what kind of model to deploy on. They can predict the model performance without actually having the model being deployed on those edge devices. So a big shout out to our team, Teresa, Zaid, and our interns who have helped us on this project. And for more details, we have a paper that's on ArcSci, and we have just presented the work at IEEE yesterday. So I'll stop here. Feel free to ask any questions.
Yeah, thank you. Yeah, Andrew. Again, let us know if you had any questions. This has been a work to show what can be done with, I guess, current mindsets, tailoring to some of the more modern needs. There's obviously room to improve on the algorithm and things that it can do, but I think the goal was to really show that there is that flexibility that you can have any number of goals and any number of resources fed into the actual model building process and not have to wait to get a model that's all trained and then try to figure those resources and constraints at the end of the day. Oh, it says, can we get the speaker's LinkedIn or Twitter? Yeah, I think yeah, I guess, Yao, Andrew, if you want to share your LinkedIn right now, we can. I was gonna also copy paste the archive link. So this is. Okay. So I pasted the link to the paper.
Just a quick reminder for folks who want to ask questions, please feel free to either post in the Q&A, or if you prefer to speak to ask questions, raise your hand. I can unmute you. You can speak to ask. We have a few more minutes. we have one question coming.
So it's from Kyle. I'm going to read it loud for everybody. So it's very interesting. Thank you for this AutoML approach. Might you share about how NAS and transfer learning address model complexity resource relative to some of the work on architecture-aware knowledge distillation approaches to train student models from existing models? Okay, there's a lot of interesting stuff in there. Okay, let me break it down. About how NAS and transfer address model complexity. Okay. So that's an excellent question. I think the current effort, we again, like the experiment that Yao and Andrew spoke, we essentially defined the basic complexity of how we want to build it. Think about, like, we defined what the brick of a wall look like. And there was not enough time to go into the depth of what these building blocks are. And Yao, feel free to chime in. But we defined that, and this is kind of where the subject matter expertise come in. And we made it part of the hyperparameter search space. But if your question revolves around if our model minimizes the complexity inherently, I don't think so. I think the model really is looking for just the goals that are predefined, like honoring the memory consumption, which is, again, proxy or correlated to the size of the network, but at the same time making sure it's accurate enough. But we agree there are a lot of other approaches. I think in the NAS community, neural architecture search, there's a lot of interesting work on how to even design the architecture in a certain way using like similarity scores or metrics, which in fact we could also infuse it in our approach. We could define some complexity score and make it as another objective. But that's again up to the human expert how they want to define that. I hope I answered your question. If not, please let us know, and we can follow up. This seems like a very good question.
Yeah, just to echo what Mohammed said, that I think kind of a key contribution, or the way that we wanted to push this problem, is to think about, can we reframe the problem into a workflow that we can incorporate constraints and add the multiple objectives. So I can imagine that there are many ways to do NNS. Is it possible to look at their workflow and to see if there's some kind of like commonality we can get from there, and use our approach to incorporate the constraints and objectives into the known process. So the transfer learning and the building blocks approach are kind of two examples to show how we can kind of merge or incorporate the known process and the model and the objectives and constraints. But there are actually, like, we encourage people to like think about other components, because the process, we can definitely work and improve on the process.
Yeah, thank you, Yao, and I appreciate the question. I invite others too, because this is really a very wide area, and there's a lot of different perspectives. So Kyle, Marley, if feel free to follow up with us. We shared our emails or link on LinkedIn, and we can get into more of an in-depth conversation. And I think the second question I'm going to read out loud is, will AutoML replace data scientist ML engineer roles? That's something that we have been joking with our boss, Teresa Tong, managing director at Accenture Lab, that she actually recently got to CTO of cloud first at Accenture. And we were talking about, like, if Yao, Andrew, and I are making solutions that will give our jobs away in a couple of years. I think this is a personal question, and I'm going to share my opinion. Andrew and Yao, you can share yours. I'm going to say no. But remember, we are always good at building systems that remove automation. So anything that, to remove repetition. So anything that you feel like you're doing 10 times, 20 times, and it's almost identical, even if it's in the ML world, machine learning, data science, yes, AutoML can remove that. but it doesn't mean you already saw there's a lot of interesting decisions that a human has to make, and those roles I still don't think is going to go away. But Andrew, Yao, you guys are also experienced there, so I'll let you speak on your behalf.
Yeah, I'll just say that I think inherently these tools end users is data scientists and ML engineers. So I think, at least for now, these should make our lives easier, not be necessarily replacing our jobs, because I think it still requires that expert knowledge of how to utilize these tools. I also want to answer the next question. So the question is, if I understand correctly, or skip to the question, you need to have a model architecture in advance for RA-AutoML to find parameters to satisfy the constraints, or does RA-AutoML can it suggest model architectures? So the answer is both. It depends on the way you configure the experiment. So the two experiments that Yao showed are actually the two scenarios that you're talking about. So the first one was a transfer learning case where we did give it a defined architecture, but we gave it more finer tuning variables to play with, such as learning rate, dropout, etc. But in the second experiment, what Yao did was give it these basic building blocks of ResNet blocks and tell it to, well, here's like one Lego brick put together, you know, a castle, right? And that's essentially what she's asked it. In that case, she is actually building, or the RA-AutoML is building the architecture, and actually do both simultaneously as well. If you want to give it a harder task, but in that case, you do need to give it more direction as far as your constraints and your objectives go, so that it does have a direction to move in.
Yeah, I would say our current approach does need to have some kind of basic architecture to begin with, right? So the very easiest one is we have one known model and we wanted to do a transfer learning to fine tune the hyperparameter, right? So we have the model to begin with, we do the hyperparameter tuning. Second is that we have a bunch of candidate models and we wanted to find what would be the best model and how do we get the hyperparameter configuration automatically. And third level, which is what we have tried to do, is using the basic building blocks, which we actually we coded, we used ResNet block and we also coded some of the basic blocks ourselves. Also has some kind of architecture inside the block to begin with. So that is our current approach to this. I'm sure there will be ways to improve on it. And goes to the next question, briefly comment on the use of Bayesian approach for search as compared to other methods like RL and GA. So the reason that we use the Bayesian approach, first, the problem started when we were thinking about hyperparameter tuning and thinking about how to incorporate constraints to it. So we configured this modified Bayesian optimization for it. That seems like a good solution for our problem here. Do you guys want to talk about the other? Yeah, so that's kind of the original motivation for us to choose Bayesian optimization.
So just want to add to what also Yao said. We're not saying any of them are better than the other per se. They each have their own advantages and disadvantages. Just to reiterate what our team said earlier, the reason we chose is some of the shortcomings of gradient descent, especially dealing with high dimensional search space that also deals with different variable types like categorical or nominal or integer, and also like continuous. So that Bayesian optimization, it can be a lot more robust. Plus, it can also help you like learn as new data point comes in without redoing a lot of things. But we know that RL is also used in neural architecture search. RL, reinforcement learning, is a big proponent these days in genetic algorithms. So as you saw, our algorithm actually uses genetic algorithm combined with Bayesian optimization because of the power that it has for the sense of extrapolation. Very interesting, actually, each of them, if you can harness the power of each method. And I think going back to the earlier question, if there's no other question, I think Andrew and Yao, do you want to talk about if AutoML replace data scientists? Because I gave my opinion. I want you guys to also speak on your behalf.
Well, I gave mine, so I guess Yao can give hers.
Okay.
I think the AutoML replaces the part that requires a lot of like babysitting work for data scientists. So I remember that when we are like doing the hyperparameter search, I will have like multiple jobs running, right? And every once in a while, I'll go see the performance, and some of the jobs I will kill very early on. Some of them I will let them run for quite a long time. And after running the model for like sometimes even a few days, I would know what would be the best hyperparameter to use for a certain model, right? So I think that is the component, that is the part that's very costly, and that doesn't require a lot of like interpretation or decision making. And this is the part that we intend to solve using AutoML. As data scientists, we have basically like a lot better job. Like there are areas that requires interpretation, gaining insights to actually figure out what kind of data to use, what kind of insight that we can get from data. How do we use the insight in business problems? And I think those are the areas that requires more like human effort. So quick answer is no, it will not replace. It will just make the make their lives easier so that they have time to focus on more important things.
Fantastic. Okay, I don't see any other questions. Thanks for a lot of interesting questions, very engaging, and thanks for your time. I'll hand it back to you,